Okay, this is a video going over one of the fencing type problems, which was in the quadratic unit. So here's this situation. Miss Jensen decided to put a dog play yard in her backyard and open a doggy daycare. Why I would do that? Like I'm not busy enough. She wants to separate big and little dogs. She does not need fencing on the side that is adjacent to the house. Miss Jensen only has 100 feet of fencing to use. She wants to maximize the area of the play yard. What are the dimensions that will maximize this area, and what is the max area? All right, so I drew a little picture for you, and you see the house there and then this play yard. And the first thing I'm gonna do is just give some labels to my dimensions here. Okay, so this is a type of problem that I'm constrained by the amount of fencing. So I'm gonna first write down my constraint equation, which is 3x plus y, based on my labeling, equals 100. And keep in mind here, x is a dimension on my graph and y is a dimension on on my play yard. My goodness. All right, so that's my constraint equation. But the equation I really want to work with is the area equation. And area of this rectangle is just x times y. Now, in order to work with this equation and to find the max, I need to write this equation in terms of one variable. And that's where the constraint equation comes in. So it looks like y is easiest to solve for here. It really doesn't matter. You just want to write, again, the area equation in terms of just one variable. Okay, so when I do that, it looks like I'm going to be writing area in terms of x. I substitute for y, 100 minus 3x. So area in terms of x is going to, if I distribute and just order it from highest degree, I'll get negative 3x squared plus 100x. Which luckily is a parabola that opens down. And the vertex is the max. Just be careful here. The x-coordinate of the vertex does stand for the x dimension, because we wrote the area in terms of the x dimension, but the y-coordinate of this vertex is the max area, not the y dimension. So let's find that x dimension. So x is negative b over 2a. So 100 over 6, or 50 over 3 feet. Now to get the y dimension, I've got to go back to the relationship between x and y. So the y dimension is 100 minus 3 times 50 over 3, or 50 feet. Now, there's two ways you could find the max area. I could plug 50/3 back in for x into the a of x equation I have here, but I actually think it's much easier. Just now that I have the two dimensions, let's just multiply them together. So the max area is going to be 50 over 3 feet times 50 feet, which is going to be 2,500 over 3 feet squared. So that's your typical max-min problem involving quadratics with a constraint equation.